Polly, Raju, can you please mute yourself?
Yeah, sure, ma'am.
Yeah, sure. So I will wait 5 minutes and then we'll start. So I think we can start. Am I audible to all? Okay. So this is week 4 tutorial session. So first we'll do some MCQ based numerical questions and then we will do some numericals. So in this week's lecture you might have covered about DTT diagram, about the part effect to particle sizes, about some interdendritic spacing during the solidification. So first we'll do some MCQ and then we'll do some numericals. So the first question is like at lower temperatures below the nose, the TTT curve is shifted towards longer time, shorter time. It is time independent and cannot be set. So we are basically talking about TTT diagram, which is like this. So we have a temperature versus time plot. So we have a time and we have a temperature plot like this. And here we have a melting point somewhere like here. So the characteristic TTT curve looks like this. It is a C curve. It looks like this, where we have a starting point for the curve and we have a end point for the curve. That means the solidification for the substance will start along this curve while the final stage will be achieved by this curve. So between this curve the particles will be solidified or they will be growing to form a solid. So we have a characteristic TTT curve. So in this question it is asked that if you lower the temperatures below the nose, this is the nose of the curve, this is called as the nose of the curve. Below the nose of the curve, the TTT curve is shifted towards longer time, shorter time, or it is time independent and cannot be set. Can you answer that? Or what could be the answer? Anybody? Can anybody answer what would be the answer? It will be shifted towards longer times. Why? Why we are saying it will be shifted towards longer times? Because when we are moving below the nose, this is a nose point, and when we are moving below the nose point, when we are decreasing the temperature, we are seeing that the solidification temperature will be the time that will be required for solidification will increase. Initially, the time that will be utilized, the time required for solidification will be quick. That means in a smaller time, the solidification will be achieved. But after a point, there will be a longer time required for the solidification. So as you decrease the temperature, a longer solidification time is required. Now we have another question that says that atomic structure is more ordered in a amorphous phase, microcrystalline phase, grain boundary phase, or a glassy phase. So by ordered structure we mean that we have a repeated units. For example, if you have a unit atomic arrangement like this is repeated throughout the lattice or throughout the microstructure. So which is the right
Ma'am,
answer?
can you explain the question number one?
The question number one says that if you are decreasing, because this is a characteristic TTT curve, this is a temperature versus time curve, and it is saying that if you at lower temperatures below the nose, so what is the nose of the TTT curve? This is the point of the nose of the TTT curve where it is curving. So this is called as a nose of a curve. So the question asks, if you lower the temperature, if you are going below this nose temperature, what will happen to the time? How will you read the time axis? You can see that as you are decreasing the temperature from below the nose, the time required for solidification is increasing. So there will be a longer time required for solidification. So this is a curve that is basically related to the transformation, how the transformation will happen from a liquid to a solid. So this curve tells you how the solidification starts from this point and then it ends on this point. So this range between this curve will let you know that there is a certain time and temperature region where the solidification will occur. So as per the question, the lower time temperatures will result in larger times for solidification or for transformation. You just have to read the axes, the temperature and the time axes. Is it clear?
Yes, ma'am.
Okay, so the second question is atomic structure is more ordered in which of the following? The amorphous phase, the microcrystalline phase, the grain boundary phase, or the glassy phase?
Microcrystalline.
Okay, so the microcrystalline will have more ordered structure, which is right because the amorphous and the glassy phase are like they do not have any specific arrangement of the atoms. The atoms are randomly distributed. So while the crystalline phase is having a ordered set of structure. Also in the grain boundary phase, we have a different atomic arrangement near the grain boundary. So it is more ordered in a crystalline phase. Now the next question is, in a time temperature transformation diagram, the cooling rapidly before the nose of the curve results in a crystalline solid. Cooling beyond the nose gives rise to a glassy structure. Cooling beyond the nose gives a crystalline structure, and none of the above is true.
That's cooling beyond the nose gives a crystalline solid.
Yes, it gives a crystalline solid. So how do we do this? This is a characteristic time temperature diagram. So basically what we say, how do you determine the cooling rate? This is a curve for a certain powder or for a certain solidification that is happening, and then you will determine the cooling rate by how you will be changing the temperature with respect to time. So the cooling rates
So
can
draw
vary.
the line.
This will be one cooling rate, this will be another cooling rate, and this will be another different cooling rates based on how much you are changing the temperature with respect to time. So here he is asked, with cooling rapidly before the nose of the curve results in a crystalline solid. This is not true because the solids are only formed after the transformation has happened, that is towards the right hand side of the diagram. So before the nose there is no solids. So the first option is wrong. The second option is cooling beyond the nose gives rise to glassy structure. So if you go beyond the nose, that this is the nose of the curve, if you go beyond the nose, that means you are having a very like high cooling rates. So that will result in the crystalline structure. So based on that, you will have a crystalline solid and not an amorphous solid. Because for producing a glassy structure or amorphous solid, you should not give enough time for the structure to form a crystalline to form an ordered or packed structure. So if you're giving it a long time, then it will form a crystalline solid, which is possible if you follow this curve. beyond the nose of the curve. So that will be crystalline solid. Then we have next question for picking sample from a powder. Where will you pick the sample from a powder container? From the bottom of the container?
Middle of the container. So we mix some samples and take the samples from several parts.
Okay. So what do you say if you, for example, if we say we have a container, we have particles inside it, right? We have a different types of particles. But when you're talking about powders, there is one problem with the powders. Like if you are taking a sample from this container, there will be different because when you're talking about particles, there are two things. One is called as a particle size, and other is the particle shape. And one more thing, if there are two or more type of powders mixed together, then also density. Okay, so for example, if you have a container and in this container you have a powder of, say, one powder is of copper, which is a metal, and another powder is of, say, for example, alumina, which is a ceramic material, and it has a less density. So the copper has high density, aluminum has a low density. Okay. So when you are mixed, for example, you have a mixture of this powder in a container. When you are trying to sample it from the container, if you pick it from the top, it is more likely that it will be rich in alumina. Why? Because its density is low. So the less denser material will be at the top, while the heavier denser material will be at the bottom. So if you take either from the bottom or the top, you will be biasing the sample. You will be creating a bias in the sample because you are trying to take only one type of a particles out of the powder mixture. So this is not the right method of taking the particles. Even if you are taking from the middle of the container, that is difficult. That is also difficult to narrate because this will help. This will create. If there is, for example, a different types of a particle shapes, you will be having a non-uniform mixture of the particles taking out from the container. So the best method is that you mix the sample after taking from several parts. There is one method that is called as rifling, where you have a rotating cone type of a disc where which rotates, and then you sample it, and from each sample you take from each cone you take one of the sample and then mix it. It is called as, one method is called as quartering and coning method. So if I
Then how to collect the samples from the bulk materials?
Yes, if you have a bulk material, then how will you do it? You will go for quartering and coning. Say, for example, you have a powder that is present in the container. You will let it fall in terms of a heap. It will fall like a heap, and then you will get a mix of a one heap here. From the heap, what you will do is, for example, this is a heap that you have got. You will try to divide it into four parts, coning and quartering. So you are divided into four quadrants. So you will take this sample out, one of the quadrant, and then again you will take rest of the three quarters and then mix it, form a heap, and again take a quartering and again quarter it. So once you are quartered it, you again take this quarter. So you mix these two quarters and then you can get the sample. This is a like in the more of an automatic process where which is referred to as coning and quartering. So I'll write it. This is called as coning, CONING, and quartering. So you are quartering the samples. So this is the best method to get samples out of the bulk. From the bottom you should not get it because there will be a difference in density, difference in particle sizes. So you will have a bias sample, not from the top, not from the container, but you can take from several parts. That is what I said. If you take from several parts, you can do this coning and quartering method to take it from different positions and then mix it. So that is the best method to avoid biasness in the sample.
Ma'am, what is exact mean of coding, ma'am?
Coning means that it is being led, the powder material is being led to fall in the form of a heap. So you first form a heap.
Like a pile up of powder.
Yes, yes, pile of the powder. It will form a heap, and then from the heap you will be quartering it.
Okay.
Okay. So then we have uh, one question that says during the convective cooling, the cooling rate is affected by specific heat capacity, Poisson's ratio, surface area, temperature difference with respect to the ambience. Which one of the following is true for a convective heating? And then we have a set of options, so you have to tell which option is right.
With the surface area.
Okay, which varies with the surface area, that is one. So you have surface area. Also, you have temperature difference with respect to ambience, and any other factor. Uh, but there is no other, no option for this, right? That means there is one more option that you are missing.
Specific heat capacity.
Okay, the specific heat capacity. This is right because what happens during the convective cooling, if you have seen the equation, that is dT by dt, which is the change in the temperature with respect to time, that is the cooling rate. So that is dependent on something. The factor is like this, where we have specific heat. It is inversely related to specific heat. It is related to diameter of the particle. It is also related to the density of the particle. The equation is like this, and then there is a difference, like there's the heat conductive difference between the temperatures, and so on. There's a equation, but in this equation there is a dependency on these factors. It says that it is dependent on the specific heat capacity, which is Cp. It is dependent on the surface area, which is also related to the diameter of the particle, so d. It is also related to the temperature difference, and that temperature difference is given here. So this based on the equation of the convective cooling, you can say that it is dependent on these factors. So you will have 1, 3 and 4. So this will be the right option. Is it clear? This is just based on the equation of the convectivity. Then we have one question which says, which of the following statements is incorrect? The particles of size 800 micrometer will cool rapidly than particles of size 200 micrometer. Particles of size 400 will cool rapidly than particles of size 800. Cooling rate is dependent on particle size. Cooling rate is directly proportional to the particle size.
1 and 4, ma'am. The particle size is 800 micrometer will cool rapidly than particle of 400 micrometer. The cooling rate is directly proportional to the particle size. These two are wrong statements.
Okay, these are wrong statements. So what is the right statement, where we can see that if we, for example,
Second and third, ma'am. As the
the
particle
correct,
size 400 micrometer, yes, ma'am.
right. So what we have, for example, we have particles like this. This is this 800 micrometer particle. So I'll write this is 800. This is 400. Then I have also small particle which is of say 200 micrometers. So which one of these will cool first? Based on your assumptions, which one will be the first to cool?
200, ma'am. 200,
The
200 micrometer
right,
particle
the
cool
200
naturally.
micrometer will cool first, because as we saw in the convective heat reaction also, in the equation we saw that there is a dependency with the diameter or the particle size. So if we have a smaller particle size, the cooling rate will be high. So this for 200 micrometer, the highest cooling rate will be there, followed by 400 micrometer and 800 micrometer. So this is right. That means the particles of 400 will cool rapidly, then particles is correct. Okay. And then also it is saying that the cooling rate is dependent on particle size, which is also right. But it is here saying that cooling rate is directly proportional to the particle size, which is wrong because it is indirectly proportional to the particle size. Well, for this, we saw that the finer will cool first, then the coarser particle. Is it clear?
Yes, ma'am.
Okay, so this is wrong statement. These two are correct statements. So then we have next question, which says atoms are generally arranged in an orderly manner when the cooling rate is very high, moderately high, at equilibrium cooling rate, none of the above.
I think moderately high, ma'am. High, very high, we can form a glass structure
Okay, for moderately high, what will it form?
with a crystal. Sorry, ma'am. It's at equilibrium cooling rate, it will form crystal structure.
Correct. So it is the structure that you saw in the TTT diagram right now, which was this structure like this. The cooling rate, if you follow this cooling rate, This is an equilibrium cooling rate. This is not a very high or a medium cooling rate, but this is what you expect. This is expected from a TTT curve, that if you follow this characteristic cooling curve and you pass the nose and the initial and the final stage of solidification, then you can achieve a crystalline solids, right? So the right answer will be at equilibrium cooling rate. You can get a arranged orderly manner, because if it is a very high cooling rate, it will follow this path. So this will be a amorphous material. If it follows moderately high, so you can say it will go somewhere in between this, something like this. But here also it will not be highly ordered. It will be a mixture of an ordered and disordered structure. So this will not be a crystalline material. This will not be a crystalline material. Only what you will have through an equilibrium cooling rate will be a crystalline material. Then we have next question, which says driving force for agglomeration of particles is agitation, surface energy, process parameters, surface contamination. How the particles will agglomerate? Agitation, surface energy, process parameters, or surface contamination. Anybody, what is the right answer? Anybody? So, do you know what is agglomeration of the particles? Actually, when you have a powder particles, for example, you have such powder particles, they have a tendency to agglomerate. What does agglomeration mean? That means they form false bonds between them. They are not chemically bonded bonds, but there are some liquid bridges that are formed between the particles. So, for example, like this, which makes them agglomerate together, and you can see a bigger particle, which is instead actually the false bondings between the particles. So what you have agglomeration of particles taking place, and this is because, for example, this particle, this will be able to agglomerate with this particle only because of its surface energy. So it will try to reduce its surface energy, and by that it will try to get clubbed with the other particles. So in order to reduce the surface energy, it will try to agglomerate together. So you will have a surface energy is the right answer for the driving force for agglomeration. If you know, there is one powder material that is called as red mud. The red mud is a industrial waste for a from a aluminium industry, right? From aluminium industry, when you get this red mud, this is a very highly alkaline powder that you get after drying. If you let it be as such, you will see that it agglomerates together in the form of lumps. So you can see some lumps in of this red mud, but these are not the true this is not the true bonding between the particles. These are just the water bridges that are formed in between the particles, and you can remove these agglomerates by heating the powder. This is mostly done for if you have an ore material. Initially, for an ore material, you always go for heating. You will heat it for some time, or dry it for 24 hours, say for example, and that is done for de-agglomeration or removal of the moisture. So you can get a true particle size for the said material. So this is was for the agglomeration. And then we have another question which says, what are the ways to de-agglomerate the particles? Drying the powder, use of the dispersing agents, mechanical agitation, ultrasonic agitation. What will be the ways to de-agglomerate the particles? Can anybody answer? Can somebody answer the answer? Basically, we are trying to deagglomerate the particles. So if you will dry the powders, you will try to remove the moisture present between these particles. So drying is one option. You can dry it and then you can break these water bonds between the two particles. Then we have use of dispersing agents, mechanical agitation. Also, we know that mechanical agitation will help you to deagglomerate the particles, right? And also ultrasonic agitation. What is ultrasonic agitation? There is, for example, a bath where you have some ultrasounds or ultrasound waves, ultrasonic waves that are being impinged on your particles. So because of this, it will try to detach any type of a contamination or any type of a finer particles that is attached to it with the help of ultrasonic waves. So this ultrasonic waves will try to have a it is actually a pulse jet of pulse jet on particles. So this pulse jet of particles will try to be deagglomerated by using ultrasonic waves. So the right option is 1, 2nd, 3 and 4. Now we have a numerical question. First I'll read it out, you can try it and then we'll solve it together. The question says that a sphere of 1 radius is heated to a temperature of 900 degrees Celsius and allowed to cool. So we have a sphere and it is of 1 centimeter dia. Okay, 1 mm. Okay, 1 mm dia, which is, so we have some 1 mm radius of the sphere which is heated to a temperature of 900 degrees Celsius, right? So we have a 900 degrees Celsius and it is allowed to cool, assuming that the ambient temperature to be 25 degrees Celsius. So you have to cool it from 900 to 25 degrees Celsius. And the constant representing heat transfer rate per unit area is 1 calorie per centimeter square. That means you are transferring or extracting the heat from this sphere at a rate of 1 calorie. That means 1 calorie of heat or energy is being extracted from it, from a per centimeter square area in a 1 second. So this is what does it mean from this heat transfer rate. That means 1 calorie of the energy is being extracted per centimeter square of the area in 1 second. So determine the cooling rate at the instant when the heating source is switched off. So you have to find the cooling rate. So you have to basically find dT by dt. That is a change in the temperature with respect to time. So you have to find what is the dT by dt based on this question. So we are changing 900 to 25 temperature. We have the radius as 1 mm and the other thing is that we have 1 calorie per centimeter square second. So this is the heat transfer rate. I think there was a loss in the connection. So if somebody can tell me what was the last thing that we discussed? What is the last thing that you discussed? We have done this question. Was it clear? This slide number 5, was it clear? Have we done all this? Were we at the last question? Okay, so okay. So we'll start from this side only. First question was done, and then
We have to discuss third question.
okay, third question. So can you tell me what would be the answer for the third question? It says that the driving
It is surface energy.
yes, the surface energy. So basically for the surface energy, because the connection got disconnected, we discussed that it has if for the particles that are agglomerated together like this.
The agglomeration of the powder.
One second. Yes, first I'll let you know the agglomeration for the particles are basically because of the surface energy. That means the surface energy of these two particles is high and it would like to achieve a lower surface energy. So it will try to agglomerate together and form a bigger surface particle. So the reduction in the surface area is the main purpose here. So you will have a reduced surface energy for producing of the higher particle sizes. Basically, what happens as I was discussing, we have one of the material that is called as red mud. If somebody knows about it, this red mud is a industrial waste. This industrial waste is produced from the aluminum industry. So this red mud, when you see, it's in the form of a powders. Like after drying of the slurry, it is in the form of a powder material, and those powders have those agglomerates. It will be in the large agglomerated size particles. It's always found in the agglomerates. So in order to break these agglomerates, what we mostly do, we try to heat it. We try to use some sieving action because of some mechanical forces. These agglomerates break. So these are just a false idea that we can understand that these two particles are joined together, but however, they're not joined together. There is only a presence of a moisture between these two particles through a liquid bridges, and those liquid bridges result in the agglomeration of the particle. So for such particles which where agglomeration takes place, it will not give us a right characterization technique. Why? For example, if you are taking the particles which are agglomerated and you try to draw their particle size distribution curve. So for example, you try to draw a particle size distribution where you determine what is the particle size of the for example of the whole material by cumulative passing. So for example, if you draw a particle size distribution, you will get a wrong particle size distribution because you will try to see there are some agglomerates forming in the material. So in order to get the right characterization results, which will be in the form of a particle size or which will be in the form of a particle shapes, because if the agglomerates take place, you will not be getting the right shapes. So either in the form of a particle size or particle shape, you have to de-agglomerate the material, and for de-agglomeration, various techniques are available. So here we'll see some of the techniques, some of the questions. This is the next question related to de-agglomeration. It is
Ma'am, the particle shape is irregular. Is the chance to form more agglomeration?
yes, if there is a high surface energy, always there will be a chance to form more agglomerates, but that is not the only reason. The reason is also that there is a presence of a
When
liquid.
compared to spherical, ma'am.
Yes, there are chances to form a higher agglomerates. If you have seen NaOH, do you know what is NaOH? This is a sodium hydroxide. The sodium hydroxide is not when you see this is a chemical. The sodium hydroxide is a very hygroscopic material. If it will try to yeah, attain large amount of moisture from the atmosphere, but normally this chemical is not present or given in the form of powder, but it is given in the form of pellets or flakes. So in the form of pellets and flakes, because you have reduced the surface area, you will have a less chances of catching the moisture from the atmosphere. So that is how you change the shape. just before, because in powder form there will be chances that it will agglomerate more, so it will not be suitable for agglomeration. So similarly for NaOH particle, which is an example that by changing the shape of the material, you can have a lower agglomeration, or you can have a higher agglomeration based on the shape and size of the particle.
How to avoid the moisture in the bulk material storage, ma'am?
Yes, this is the question that is related to that. The question says, what are the ways to de-agglomerate the particles? So, first is drying of the powder, use of a dispersing agent, mechanical agitation, ultrasonic agitation.
Use of a dispersing like a silica gel.
Yes, silica gel is one of the options that is done in large scale, that you use a dispersing agent. You can also dry the powders. This is mostly done for example, in your ores. For if you have an ore material for any ore, initially when you crush it and form the powder, it is always heated in the furnace for like 12 to 24 hours to remove the moisture, because that will once the moisture is removed, the powder particles will be deagglomerated. So you can dry the powder for deagglomeration, because basically the agglomeration is because of the liquid bridges that is formed between the particles. So you can dry the powder, you can use a dispersing agent, you can use mechanical agitation also. If you will mechanically agitate the particles, you will also try to separate the deagglomerate the material. One option is also ultrasonic agitation. So what is this ultrasonic agitation? This agitation is like if there is this ultrasonic, for example, bath or ultrasonic water medium. You have this particle and you just want to deagglomerate it. For the deagglomeration, these ultrasonic waves will be impinged on this material. These ultrasonic waves are actually high jet pulsed agitations or pulsed radiations that are present in this ultrasonic bar. So because of these pulsed jets, the particles will be deagglomerated and you will get a separate particle size or the true particle size for the powder. So the option will be 1, 2, 3rd and 4th. All are used for deagglomeration of the particles. Now we have this question which says that we have a sphere of 1 mm radius. So what we have this sphere, the radius of it is 1 mm. Okay, and then it is heated to a temperature of 900 degrees Celsius. So you are heating it to 900 degrees Celsius and allowed to cool. Assuming the ambient temperature to be 25 degrees Celsius. So you are trying to cool it to 25 degrees Celsius, right? And a constant representing heat transfer rate per unit area is 1 calorie per centimeter square. So what does we mean by heat transfer rate per unit area? That means 1 calorie of the heat is being taken out from this sphere per unit of area, which is centimeter square. From 1 centimeter square area, 1 calorie of the heat is being extracted in 1 second, because it is per second. So this is a heat transfer rate. That means 1 calorie is being extracted per centimeter square of the area in 1 second. So you have to determine the cooling rate at the instant when the heating source is switched off. So you have to determine what will be the cooling rate in calorie per degree Celsius per second. So you can try this for like we'll wait for 2 minutes. You can try it, then you will solve it. The two is that you can do, if you never remember the formula, you can go by balancing of the units, right? So we are saying that we are required to form a cooling rate in calorie per degree Celsius per second. So since you are given that there is a 1 calorie per centimeter square, so you can write it 1 calorie per centimeter square per second. This is your heat transfer rate. And you say that you want to remove the centimeter square from the units in order to achieve the cooling rate. So what will you try to do? You will multiply it by the area of the uh, So surface area of the sphere, because we know that it is the surface area of the particle that influences the cooling rate. So because it is assumed to be sphere, so we'll multiply it by the area. So that will be 4 pi into r square. So what will be the r square, because radius is 1 mm, so we can convert it into centimeter. So this will be 1 multiplied by 1. So this is area, this is given in centimeter square. So you can cancel out these two. Now you need the temperature, which is degrees Celsius. You have to understand that because we are talking about removal of the heat from the material by changing the temperature from 900 to 25 degrees Celsius. So it would, as you know, that the heat transfer or heat extraction or the cooling rate, it depends on the difference in the temperature, difference between what is the temperature of the particle and what is the ambient temperature, which is 25 degrees Celsius. So you will have a units of 1 calorie degrees Celsius per second. So you can calculate what is the answer for this. This is actually the general formula for the like for the loss of heat or cooling rate. It is given by this dT by dt. This is also known as Newton's law of cooling, if you remember. This is given by minus K A into the difference into the temperature, difference of the temperature. So this is based on the Newton's cooling law. You can calculate what will be the cooling rate. So if somebody can answer what will be the answer, somebody has calculated it. I think that is all for today. Okay, thank you.